Before we jump into this one, please pause the video and decide which of these two pictures demonstrates poor accuracy and which one demonstrates poor precision. Pause the video and give that a try now. Okay, so let's take a look. Now this top one is going to be an example of poor precision, and that's because it's got a lot of randomness. Notice that we have our true value marked right here for 25, and we have a decent amount of deviation for each of these data points. Here we are. Notice that the clustering is a little bit tighter down here, so I'm not sure that I would call this awesome precision either, but certainly this one is all about the precision because on average it still does come out to be about the same. Notice that these arrows are about the same size, these arrows are about the same size. So we can do a measurement and determine how much random error there is and how far from a true value it is, or how much deviation there is from the average at least. Notice that 25 dotted line may not even be the true value. I'm telling you that it is in this case. But if we were to take the average of those four values, it coincides probably perfectly with the 25.0 mark. It's all about how far away the individual points are. And if you think back to what happens in math, we'd say that that would be standard deviation. Now, that means the procedure is not controlled enough. That said, what do we mean by controlled enough? We have to make the decision on each experiment. There are times where you need to spend $1 million to be sure that the average and the standard deviations are dead on and very tight for the groupings. But usually you don't. I mean, if you're building a plant to make pharmaceuticals, sure, those drugs better have very small standard deviations and they better be very precise and accurate. That's great. But you know, when you're making something like, when you're making a bath to pickle aircraft parts, or you're processing stainless steel, or you're just making sure, you're measuring how much citric acid is in lemon juice. Individual bottles of lemon juice can have a little bit of varying acidity because nobody's going to be terribly upset if it's, instead of pH 3.433, it's pH 3.444. Nobody's going to be all that upset about it. However, you're going to care a lot when you're talking about the tolerances on finely machined parts that go into an aircraft engine. We have to decide, is it controlled enough for the amount that I have to do? The amount of work, the amount of money, whatever. And so we'll often have to tolerate a certain amount of imprecision in our final measurements. As long as they're still accurate, that can still be okay. Now let's look at the bottom example. This is an example of poor accuracy. And you can see here that the average of these probably sits right about here to do it without any math. Somewhere in that range is probably our average, right? And obviously, that's a decent distance from the true value. That's going to be an example of systematic error. What do I mean by that? This is a sketch of a volumetric pipette. When we use the volumetric pipette, we know that we have to fill it up so that our meniscus sits right there at the line, and the bottom part of the dip of the meniscus meets up with the line. That's how we're going to be rating the volume. We're supposed to leave a little drop right here in the tip. If you don't, and you blow it out, what are you going to be doing? Well, since it was calibrated to deliver, this drop was calibrated. It's supposed to stay in here. If you blew it out, what's going to happen? You're going to be increasing your volume, and you're going to increase the mass of the water that you just delivered. So if you're blowing that drop out all the time, you're going to be causing a systematic error. There's something systemically wrong. There's something wrong with the system that you're using. You're doing something repeatedly, but incorrectly. That's what we're talking about with systematic error. And it doesn't always mean that you screwed something up in terms of your hands working at the bench. It could be that your technique, your laboratory approach, that the chemical that you're using to change colors at the end, maybe it's the wrong one. Maybe you picked one that gives the color change at the wrong time, or has some sort of a more complicated chemistry happening. All of those kind of things could result in a systematic error. It tells you that something isn't quite right, either design or execution.